All right, so I am going to give you an overview of the Early Release Science Program templates, which is a somewhat contrived acronym, but it describes what we're doing. We're targeting extremely magnified panchromatic lensed arcs and their extended star formation. So I'm the PI, I'm Jane Rigby from NASA Goddard. The co-PI is Joaquin Vieira from the University of Illinois, and we have a great cast of co-investigators as well as 17 named collaborators. And so the 4 targets of our program, all extremely bright lensed galaxies, some of the brightest galaxies that are known, are here on the title page because I wanted to get right to the point. The point of our, I think I can motivate our science in a couple ways. One, I can't advance, there we go, is that it's all about spatial resolution. So JWST will bring unprecedented increase in sensitivity in its most sensitive bands, a factor of 100, deeper flux limits and the same integration time than previous observatories. But you can't break the diffraction limit. That's just physics. And so the diffraction limit of JWST at 2 microns is comparable to the diffraction limit of Hubble in the UV. And so practically speaking, that means that in the distant universe, you can't resolve features that are smaller than about 300 parsecs or so in radius. And so if we look at, so that motivates our program. By targeting lensed galaxies, we can study much finer spatial scale, study star formation within galaxies on scales that without lensing are spatially unresolved or only marginally resolved. And so to illustrate this, this is on the left in the blue is a big lensed arc that we've published in a couple papers that are cited down there. And in gray in the middle is our reconstruction of what that galaxy looks like were it not lensed. So with the funhouse mirror distortion of lensing taken out. And what you see in this galaxy is 24 small knots of star formation with radii of about 30 to 50 parsecs. So this is from the Johnson et al. Papers cited below. And that is, this is a galaxy that is undergoing just fireworks of star formation. And on the right panel, you can see what that galaxy would look like were it not lensed, but were just a field galaxy, just in terms of what the blurring effect of the PSF would do. And so on the left is what it would look like to HST with the WST3 instrument. And on the right is what it would look like to NIRCam with JWST. And so you see very similar spatial resolution with JWST compared to with JWST in the near infrared to HST in the UV. So that means that's much better spatial resolution out in the near infrared than we have right now, but it's just going to be a fundamental problem for understanding distant galaxies that we're not going to resolve features much smaller than a kiloparsec unless we target lens sources. So that takes us to the idea of using lens galaxies for a sample. And so, this isn't new. There's a whole cottage industry of studying gravitationally lensed galaxies in order to study either features that are too faint to get infield galaxies or to study spatial scales that are otherwise blurred by the PSF. So these are our 4 targets from left to right. In 4 targets, we were trying to cover as big of a parameter space as possible with only 4 targets. So you can see we span a redshift range of between 1.3 and 4.2. We span a star formation rate of less than 10 to almost 1,000, or more than 1,000. And we span a range of extinction of basically very little out to 6 magnitudes. And so what we're trying to do in this program is to grab some of the very brightest lens galaxies that are known, spanning as wide a range of parameter space as we could, given the size of an ERS program, and to try to establish what do galaxies look like to JWST at these redshifts, with a number of science goals that I'll get into in a minute. I just want to mention that the magnifications for all of these targets are extremely high. For 3 of the targets, they're 20 or above. And so we're seeing spatial scales that are otherwise inaccessible to Webb. And so I've also drawn here a 3 arcsecond little bar on each image. That's the approximate size of the near spec integral field unit. And so that's part of why these sources were chosen. They fit really nicely into the near spec and MIRI IFUs. And so we can get spatially resolved image cube spectroscopy fairly efficiently. There are other lens galaxies that are much larger and longer arcs, but that don't fit into that IFU. And so from a practical standpoint, part of how we put this program together is to say, all right, look, we have to walk before we can run. Let's get galaxies that should have gorgeous spectra that we know are very clumpy. And so we have a lot of different amounts of surface brightness and brightness of each clump. And then let's see how well the IFUs perform. How well can we measure fluxes of lines of given brightnesses? And I'll talk about a little later, that's one of the really basic early deliverables we want to have, is just signal to noise versus source brightness, knot by knot through these arcs. I should also say that we have very deliberately chosen 2 targets on the left side that were UV selected as blue arcs in all sky surveys, and 2 targets that were selected in the submillimeter from the South Pole Telescope, also a very large area search. So these are very bright arcs chosen from full field, from large area surveys. These are not faint arcs in things like the frontier fields clusters. And so the reason that we've chosen 2 submillimeter selected sources and 2 UV selected sources is that we recognized that there are these different subcommunities that study either submillimeter galaxies or that study UV selected galaxies that don't have a lot of communication, in part because we seldom have data sets in common. It's challenging to get ALMA data for normal star-forming UV-selected galaxies. They're just faint. It's very challenging to get HST imaging for very obscured submillimeter galaxies. You could see it right that the HST data is shown in blue. You're seeing the galaxy scale lens, but you're not seeing the background galaxy, the arc, the lensed arc. That's just showing up in ALMA. Because of JWST's sensitivity, what our program is able to do is get apples-to-apples data sets for these galaxies that are selected in very different ways and have very different levels of extinction. And so for the UV-selected galaxies, even though they don't have a lot of dust and a lot of dust reprocessing, we can still capture the dust emission and the PAHs with MIRI. And for the SPT-selected, the submillimeter-selected galaxies, even though they're very extincted, we're confident we can still obtain the rest frame optical emission lines with near spec with JWST. So we're really trying for the first time to put the same sets of data in the hands of these communities so that we can understand more fully the complicated picture of galaxy evolution and the diversity of sources in the distant universe. And so let me just dive into science goals here and how those map to instrument modes. So if you'll please look at the right-hand column of science goals. Our science goals are pretty straightforward. Our first is to measure the physical conditions of star formation and the spatial variation of those physical conditions. And so that translates to a lot of near-spec IFU spectroscopy. So we'll be obtaining the rest frame optical emission lines, the famous Osterbrock and Ferlin, all of the classic rest frame optical emission lines for all of these galaxies. And especially we're focusing on H-alpha because it's a map of star formation rate, but we'll be getting all of the classical rest frame optical lines. So second goal is to demonstrate extinction-robust diagnostics of star formation rate. And so for that, we're going to be using Passion alpha maps from MIRI MRS IFU spectroscopy. Now, Passion alpha, and in fact, what we want to use is extinction-corrected Passion alpha. So Passion alpha maps corrected by the H-alpha to Passion alpha ratio. That's not, that can get optically thick in very dense environments, but it is widely seen in the nearby universe as the gold standard for measuring star formation rate. So we'll be obtaining Paschen alpha maps for all 4 sources. We'll also be obtaining, with MIRI IFU spectroscopy, 3.3 micron PA maps. That's the PA feature that we can get at these redshifts and traces the hot dust in these galaxies. We'll also have extinction-corrected H-alpha maps. And we have from other, we have ULMA data as well. So we have multiple ways to measure the star formation rate and just see if they agree. When we have beautiful data and lots of coverage, do the diagnostics even agree in situ in the distant universe? We have inner comparisons at redshift 0, but we really don't have them in the distant universe, especially over a wide range of extinction like in this program. Third science goal, we want to compare the spatial distribution and the evolution of the young and the old stellar populations. So with HST, we have been able to measure where the young stars are in galaxies at cosmic noon, redshifts of 1 to 3. And with Spitzer, we've measured how much stellar mass those galaxies have. But Spitzer is a 0.5 meter telescope, and so we haven't been able to spatially resolve where those old stars are. JWST will map those old stars at the same high spatial resolution as in the res frame UV from Hubble. And so at the same matched spatial resolution, we'll be able to map where are the old stars, where are the young stars. How does star formation proceed morphologically within a galaxy, inside out, outside in? And we'll be able to see how that process works and things like, do clumps persist? How much do clumps that we see in the UV forming lots of stars, do they have old stars as well? Or are they just new things that have not been around for very long? And then fourth goal, NIRCam imaging. We will be using most of the NIRCam and MIRI filters that made sense. And so we will have multi-band imaging from which we can construct spectral energy distributions on a pixel-by-pixel basis. And the goal here is to resolve that, is to make maps of the young and old stellar populations, again on these 100 parsec or a little better spatial scales, and to see the histories of star formation within these galaxies in an extinction-robust way. And I should have stressed that all of these science goals, to some extent, are possible now a little bit at the edges, but not in a spatially resolved way in the distant universe, and not in a way that is robust to the effects of extinction. So those are our science goals. I want to then transition to what we'll be doing for the community, and then I'll close. So we have here's our planned set of deliverables. We have 2 pre-launch deliverables and then 3 post-launch deliverables. The first pre-launch deliverable, we will be providing lens models based on Hubble or ULMA data. We have those pretty much ready to go, and we'll get that deliverable out shortly. And we will also be providing our high-level data from ULMA and from Hubble. For Hubble, that includes for one source GRISM spectroscopy. We have a deliverable 1A, which is also a pre-launch deliverable, where we've had more time due to the launch delay, so we're using that time to develop some simulated data, both raw or level 1 products and science-ready level 3 products. That's part for our own selfish purposes. We want to make sure our team understands how to deal with JWST data and that we're ready to go. But it also, we've committed to making all those data products public once we build them, and showing the community what we've learned about, here are some representative data sets on what bright lens galaxies ought to look like. We also have a goal of running those simulated raw data through the JWST pipeline and getting to science-ready data. So proving to ourselves that when we get raw data, we can turn it into science-ready data using the JWST pipeline. And we have also committed that when we get that process working, we're not there yet, we will publish our results as a cookbook so the community can practice along and gain that knowledge as well. We'll also be delivering any improvements to the lens model. Then let's talk about post-launch deliverables. So our delivery 2 at Launch Plus about 10 months, assuming that we start getting data shortly after commissioning ends at Launch Plus 6 months. So we will commit to releasing level 3 data products as we make them, as well as our cookbooks for how we made them. A lot of the emphasis of our deliverables and how we can serve the community is cookbooks. And so we used as a model the APES cookbook from the radio community, the Chow threads from the Chandra community. We're going to be doing them in Jupyter notebooks, so you can see the embedded code and just say, this is what we did. This is the results that we got. Tell us if you can do better. I should have mentioned that in our observing strategy, we are doing some calibrations with NearSpec that nobody really knows if we need. So if we go back to, how do I go back? There we go. So we have chosen, if you see our sources pretty much fill the IFU, where we are doing offset skies. So we're doing a dedicated sky frames for each of the NearSpec observations. It's possible we don't need that we can measure the sky background from the corners of the IFU, but we don't know that. And so we will be taking those dedicated sky frames, reducing the data using those skies, and then going back and saying, what if we just use the sky in the image? Is that good enough? So we're also taking leak calibrations. The IFU for NearSpec sees the imprint of the multi-object shutters. So there's this little faint bleed of all the shutters on top of the IFU. You can fix that by taking what are called leak calibrations, but they're time-consuming. We spent a lot of time arguing about whether to observe them or not, and realized that that was actually a service for the community. So we will be taking those offset dedicated sky frames and dedicated leak calibrations, reducing the data using them, and then reducing the data again, skipping those steps, and publishing in a cookbook what difference did it make, so that other users for cycle 2 and beyond can make educated decisions about whether they need those calibrations as well. So those are early versions of those will be in our deliverable 2. That's what we mean by cookbooks. So really, what strategies did we use to deal with the data, what worked and what did not work? We'll also be publishing some just simple plots of surface signal-to-noise ratio as a function of surface brightness for the IFUs. So in-depth look at how well can we do with the IFUs. Deliverable 3 has higher level science products, so combining multiple level 3 data products. So that includes things like maps of the extinction, maps of extinction corrected H-alpha and passion alpha, maps of other emission line ratios, source plane reconstructions from the JWST data, and ST fits. And then we have a 4th deliverable that is expected to be a cleanup of improved data products. And I'll stop there.
Thank you, Jane, for that very interesting lecture about what you're doing. And boy, the resolution you're going to get sounds really mind-boggling. I didn't even know it was possible. Is there anybody on the call who has a question for Jane? Okay, well, I am going to ask a question because I always have lots of them. But I'm thinking through your program. And you're going to have spatially resolved, all those different objects. And you talk about modeling. So when you talk about like simulated data for modeling, do people have already have models in place for these because they've been studied before, or is that something that requires? I'm just trying to understand what that requires to create something like that.
So we deliberately targeted very well-studied galaxies. These are among the best-studied lens galaxies that are known. So there are already lens models in place for these galaxies based on Hubble and ALMA data. When I say in the deliverables that we want to do simulated data, that really is, we're using Mirage for NearCam, we're using the MiriSim for MIRI, and we're working with the NearSpec team to try to create some custom NearSpec simulations because there's not a public NearSpec simulator. So those will be in the image plane, so distorted because of the lensing. They're modeled based on what we already know about these targets from Hubble and from ULMA. And then some reasonable simplifying assumptions about, say, what their spectrum might look like.
Okay, so you have some assumption about, I was thinking a little bit about Elle's program, where she's kind of getting spectra of sort of these different types of regions, but maybe they're templates for star formation regions and things like that, that you insert and you kind of add all together.
Yeah, so we are, for our program, based on the photometry, making assumptions about the spectral, about how bright the spectra are. And then, yes, using some template spectra. And of course, in many cases, we don't know what the actual spectra are, or what we have now is a ground-based spectrum that's not spatially resolved for most of these. And so we have to, that's why we need to go measure them, to measure how those things actually vary spatially.
Okay. And just to ask you the question, because you're doing spectra of these regions, not just imaging, do you expect to discover anything new spectrally, that hasn't been seen before?
Oh, that's a good question. So we set our integration times based on the flux in H beta. So these are not incredibly deep observations. The near-spec data are a couple hours deep per target. Same for MIRI. They're pretty shallow because they're very bright targets and because we were trying to fit 4 targets into an ERS size program. So I would expect for some of these lens galaxies, if you integrated a fair bit deeper, then there's the possibility of doing very faint emission lines, including ones that have not been seen outside of galaxies with Messier numbers. So things like the auroral lines, which is a way to measure metallicity by counting ions instead of through empirical calibrations. I think that for the lower redshift sources, we can measure the PA features like in Elle's program, but at redshift 1 to 2 rather than in Orion. And I think there are doubtless surprises about how the dust has evolved with time that a good MIRI spectroscopy will reveal. You can't do as high redshift as you'd like just because of MIRI cutting off at 30 microns and the brightest PA features being at 8 microns. But in the sort of redshift 1-ish universe, it's totally doable. And I mean, we did some of that with Spitzer, with lens galaxies, and it looked really cool. There's very strong evolution in the PA features between redshift 0 and redshift 2 of high redshift ultraluminous galaxies. But none of it, of course, is spatially integrated. And it was all at resolution of 100, which is what Spitzer delivered.
Yeah, well, I'll certainly be interested in hearing about that.